This is a little tutorial on projectile motion, so you can understand how an object moves through space when it's thrown or when it's dropped. So this right here represents the path of an object that was thrown up into the air. Here it reaches its maximum height, and then here it goes down and hits the ground. So in this case, the x-axis actually represents the position of the object along the sideways axis. It's not time here, it's the position. And y represents, of course, the height. So the blue arrows are showing the velocity vector of the object. It means the direction it's actually going at that exact moment and its speed. So you notice at the beginning the blue arrow is quite large and it slows down. It's not so big right here when it hits the top, gets to the top, and then as it goes down it speeds up. And that velocity vector is always at a tangent to the curve. A tangent line is where it just touches with one point. But that blue velocity is not something you need to be worried about right now for analyzing the motion of the projectile. In our science class, we're going to break that down into its two little components. Each of these blue arrows, if you looked at it on a vertical axis and a horizontal axis component, can be analyzed as a red arrow here going up that represents the changing vertical speed direction. And then the green arrow represents the horizontal component of the velocity. And you notice quite quickly if you study these, all the green arrows are the same length. And the red arrows are different lengths. So that tells you something. It tells you that the horizontal speed is constant, but the vertical speed is changing. So that's interesting. So when we look at this little projectile motion paper that I gave you, it tells you here that the forces affecting a projectile, not a self-propelled rocket, are gravity and air resistance or air friction. Okay, and remember that it's very important to understand that it's only unbalanced forces that change an object's motion. So if forces are balanced, like if something is squishing on both sides, like say here's a ball, and somebody's pushing on it one side and pushing it on the other side, equal and opposite, it's only going to experience compression force. It's not going to change its motion and go sideways. Anyway, what was I saying? Oh yeah, so for horizontal position, you can calculate that using this equation, which really represents the distance that it goes horizontally, that's x, equals the rate, the horizontal speed, times the time. And that tells you how far sideways a projectile goes. And remember that since that horizontal speed here, that green component, is constant, you can do this then. With a constant speed times the time, that'll give you this distance that it travels in the air. Okay, so let's look at the next section here. Let's see, where are we? Vertical position. So for vertical positions, the y changes as a function of time. We say that y is a function of time, and so the equation is showing a sub g, the acceleration due to gravity, which is 9.8 meters per second, and then v naught, which is the initial vertical speed upward, and that's caused by the force that was launching the projectile in the first place, and then y naught is how high it was to begin with. We take as a convention that up is positive, so the upward direction is positive, that's an up arrow, downward would be negative, and I will continue this video, and we're going to need a part 2 on this video.